So we sort of switched gears last time from talking about sort of physics of climate and the atmosphere a lot to talking about the carbon cycle. So this is kind of coming at the same question of possibility of human-caused climate change, but now from a completely different sort of a direction, and that's where we're going to continue going today. And I talked to you last time about a feedback mechanism in the carbon cycle that has to do with volcanoes releasing CO2 to the atmosphere and a process known as chemical weathering, which is given by the Urey reaction, where we have basically igneous rocks, which are the crystalline rocks on the one side, and sedimentary rocks on the other, and CO2 is part of this. So the CO2 reacts with the igneous rocks and winds up making calcium carbonate and silica, which are on the bottom of the ocean. That's where they end up. Those are two major components of sedimentary rocks. And then ultimately the calcium carbonate gets subducted and cooked and turned back to CO2 and released to the atmosphere. So there's a sort of cycling of CO2 out of the solid Earth here and then into the solid Earth there. And so to get the eye clickers going, the first thing I wanted to sort of get out on the table is positive versus negative feedback. And most of you are getting that right. It is a negative feedback. So negative feedbacks are the ones that stabilize things. Positive feedbacks are the ones that amplify things. So this is a thermostat, so it's a negative feedback. And another negative feedback is this sink analogy that we talked about. We used we used it as an analogy to other situations. We used it as an analogy for the energy coming into the planet and leaving the planet. And when we used the analogy for that, the water level in the sink was the energy that sort of accumulated in the planet, which is the temperature, because the temperature is just the thermal energy. And if you made the temperature higher, that means that the energy leaves the planet more quickly, according to epsilon sigma t to the fourth. And so that's like the water level in the sink makes the water go down the drain faster. So the analogy sort of fit that negative feedback. So the question is, does the analogy work again for a different, totally different sort of a situation, a different negative feedback? And can we use it? So if we did, the water level in the sink, that would be what part of this would that be? Would that be the global temperature? That's what it was before when you used it for energy balance, but we want to use it now for the carbon cycle. Would it be the flux of CO2 coming out of the Earth from volcanoes? Would it be the atmospheric CO2 concentration? Or would it be the rate of chemical weathering, which is the igneous rocks going to make sedimentary rocks? Or do you think that I'm just kind of screwing around with you and it doesn't actually make any sense, this analogy? Nobody thinks I'm that evil. Only one person. I'm sorry you think that, but most of the rest of you are getting it right. The water level in this analogy would be the CO2 concentration in the air, and so the water coming in from the faucet in this analogy, we've got the same choices here, and It looks like choice B is making a run for the money here, as fast as the clickers can record it. And yeah, that's true. So this is volcanoes. The CO2 from volcanoes. So the water flowing into the sink is kind of independent. It's like an external driver. You know, the water flowing in from the faucet doesn't care how much water is in the sink. In the same way, the CO2 coming out of the earth doesn't care how much CO2 is in the atmosphere. It's like this external driver that everything else kind of has to comply with. And then the water going down the drain is, there we go, the rate of chemical weathering. Yeah, so, I mean, in one sense, that's kind of simple because, you know, it's the way that CO2, we already decided that this is the CO2 in the atmosphere. And the way the carbon leaves the atmosphere to go back into the solid earth is by this weathering reaction that takes the CO2 and the igneous rocks and the carbon ends up on the seafloor. So it's basically gone back to the solid earth by this. But it also kind of fits the analogy in that it's the rate of weathering that provides the feedback. The rate of weathering is a function of the temperature of the earth. Well, it's a function of water. Water runoff. So in order to dissolve a rock, you've got to have some water to dissolve it in. So the more gallons of water you have washing over the rocks and then flushing out to sea, the more gallons per year or whatever, the more rocks you can dissolve. And so the more of this chemical weathering reaction you do. And so the CO2 runoff is a function of the temperature. A tropical world has more rain, and there's much more runoff from the Amazon because that's a tropical climate than there is from the Yukon. The number of inches of water running off every year is much higher in the tropics than it is in the poles. And if the whole planet were much warmer, there'd be more runoff. And then temperature of the Earth is a function of CO2. So now we've got a link between the weathering rate, which is the sink. By sink I mean the way that CO2 is removed back to the solid Earth. It's like the water flowing down the drain depends on the water level. The rate of weathering depends on the amount of CO2 in the atmosphere. So it's a quite ideal application of the same analogy, but just to a totally different situation. So does anybody have any questions about this weathering feedback? We spent the first half of the quarter talking about why climate could change if the CO2 concentration changed, and we read the terrifying 6 Degrees book. And now all of a sudden I start telling you the Earth acts, for what it's worth, like a huge organism, homeostasis by and for the biosphere, can regulate itself, negative feedback, controls atmospheric CO2 concentration. Does this spark any curiosity? Any question about this? Sorry? Because the Earth can take care of itself, right? So the question that you would ask before you feel totally better is, what question would you want to know? Okay, quickly enough, right? Quickly enough. Yeah, that's the issue. We said that this sort of thermostat, as a function of time, there is some CO2 concentration where the influx equals the outflux. So that's kind of the set point of the thermostat. And if it's too high, it will go down. And if it's too low, it will go up. But I never put any units on this time axis here. So before we get too complacent, I should probably do that. And the answer actually is going to disturb your good feeling. It's going to make you feel just as doomed as you felt before, because the time scale for reaching the equilibrium here is kind of slow. It's kind of on the order of 100,000 years is sort of that amount of time. So it's a thermostat, but it's not a particularly useful one on a human time scale of our lives and our children's lives and things like that. But it does help explain the sort of spooky intrinsic stability of the Earth that we see, the faint young sun paradox. It explains all kinds of things, and it sort of sets the stage for the sort of global warming climate event that we're going to talk about. So there's some other sort of epilogue kinds of points I want to make. We talked about our truly doomed sister planet, Venus, when we were talking about water vapor feedback and the runaway greenhouse effect. So there was a runaway greenhouse effect on Venus that is, you remember, it's where the water all goes into vapor. So the Earth isn't going to have a runaway greenhouse effect, because if you put too much water vapor in the air at sort of something like Earth temperatures, it'll just rain out eventually. So you can't put more than a certain amount. You can't make the whole atmosphere more than 100% relative humidity, or else it'll just sort of rain out. So we're kind of protected by that behavior of water vapor. But Venus, closer to the sun, managed to escape that. All the water on Venus went into the atmosphere, which made it very, very hot. But then the hydrogen, the water in the upper atmosphere, got blasted into atoms by ultraviolet light in the upper atmosphere. So it lost all of the hydrogen and lost all of its water forever. So a runaway greenhouse effect like that is a total one-way street. There's sort of no recovering from that. But now that we've talked about the Uri reaction and the silicate thermostat, we can take this whole disaster one step further. So the Uri reaction, again, is here, and remind you we have sort of a high temperature end wants things to be on this side. So the high temperature, you take this collection of elements and you cook them at high temperature, and the CO2 wants to go into the gas phase, because gases like to be free if they're at high temperature. And then there's this sort of low temperature end on this side, and then this thermostat is this sort of tug of war between what the deep earth wants and what the surface wants, whether the carbon should be in rocks or whether it should be in gas. But we also know that this weathering reaction, to dissolve this igneous rock and then make the sedimentary rocks, it needs water. So if you got no water, you got no weathering. So So this is what happened on Venus. All the carbon that Venus has, or most of it, goes to CO2 in the atmosphere. So that's why the atmosphere of Venus is 70 atmospheres. We have 1 atmosphere of total pressure on Earth, of which most of it is nitrogen and oxygen, and there's a little bit of CO2. But most of the carbon on Earth is in the form of these calcium carbonate rocks. On Venus, the thermostat broke because there's no water, and so the low temperature end, you can't get to the low temperature end, so forget about it. There's no water, you can't do this chemical reaction, so the high temperature end wins on Venus. The high temperature end says that carbon should all be in the form of CO2, and so you end up with 70 atmospheres of carbon dioxide in Venus. Actually, just as a sort of by way of curiosity, at high enough pressure, there ceases to be any difference really between gases and liquids. You get something called a supercritical fluid, and that's the way it is on the surface of Venus. The CO2, it's almost not like an atmosphere because it's sort of not gas. It's more like this weird supercritical fluid. And so really the atmosphere of Venus is almost more like an ocean that kind of grades into kind of an atmosphere higher up. So losing the water is how this thermostat mechanism on Venus broke. And then there's our other sister planet is Mars. And the problem with Mars is that it's a smaller planet. It's about half the size of Earth and Venus, and so it cooled down more quickly. And the largest volcano in the solar system is found on Mars. It's called Olympus Mons, and it's huge. But there's no tectonic activity on Mars anymore. There's no cooking of any calcium carbonate rocks at high temperature in the interior of Mars. There's nothing like plate tectonics that can make this happen. And so there's no CO2 degassing to the atmosphere. So what has happened there is that the temperature got very cold. Cold enough that there's no liquid water, and so if there were CO2 coming out of Mars, it would just build up in the atmosphere and build up until it got warm enough, presumably, if there was enough carbon, to make liquid water, and then you could do this chemical weathering, and you could make a thermostat there, and it could hold the climate sort of at in somewhere in the liquid water range. But the fact that it's tectonically dead now means that the thermostat broke on Mars as well. Cool? I mean, is this exciting or, maybe sort of? Okay. Yeah. Now, there's tricks to this thermostat on Earth as well. And we can kind of think about it by making use, perhaps, of our sink analogy again, because there's the thermostat tends to find a CO2 concentration where the input of CO2 to the atmosphere balances the output. But there are ways that you can sort of manipulate the system, or ways that, chance arrangements of continents and things like that can sort of tweak the Earth system that can cause the set point of the thermostat to sort of drift up and down. So today, the Earth's climate has these big ice sheets in Antarctica and in Greenland. But most of the time throughout Earth history, there are no big ice sheets on Earth. So a geologist who thinks in the long term would call what we are living in today an ice age, because there are ice sheets. And of course, they were much bigger 20,000 years ago. The ice sheets have been going up and down in their size with this glacial, interglacial cycles. But the bigger picture, if you stand way back and look at the whole of Earth, Earth history, is that we have ice at all. And so we're in this sort of an icy climate, as opposed to a hothouse climate, which is where the Earth spends most of its time, with no ice on Antarctica or Greenland or any place like that, and sort of lush tropical-looking vegetation all the way up to the high latitudes. If you go see a natural history museum and look at the dinosaur dioramas, they've always got tropical-looking plants there, ferns and big leafy things. You don't see dinosaurs with except on the first Star Wars movie. You see that. Never mind. You don't see them in cold climates, because the Earth was much warmer then. The reason why it was warmer is because you can sort of manipulate this thermostat to change the set point. So it's still regulated, but it regulates it to a different value, kind of drifts up and down. So one way to change the set point might be analogous to turning up the water coming out of the faucet. So that would change the water level in the sink. If you turn the faucet up, that means that you have to send water down the drain more quickly, and so the water level in the sink builds up. So if we were to increase the rate of CO2 degassing from the Earth, from volcanoes, how would that affect the temperature of the Earth? I should let you know that the problems for lab next week involve a model that play with this. So you're gonna see all of this again next week in lab. But yeah, you're basically getting the right answer here, that when if you were to increase the rate of CO2 degassing from the Earth, that means that you have to weather more, and the way to weather more is to have a lusher, rainier, wetter world, which means more CO2 in the atmosphere. So the way actually it sort of works, we'll talk about this again when we talk about fossil fuel CO2, but the calcium carbonate at the bottom of the ocean. So here, imagine this is ocean crust. So it forms in the spreading centers, and then finally it subducts in, after the crust is a couple 100 million years old maybe, and it's cooled down and it gets dense enough and it sinks and it sort of goes underneath some other plate of crust. So here's the subduction and here's the spreading center. The way calcium carbonate tends to work is it tends to deposit mostly in sort of on topographic highs. It's like snow-capped mountains. If you were to stand and look at mountains like Mount Kilimanjaro or something I saw pictures of the other day, there's snow up at the top and nothing down below. Calcium carbonate is sort of that same way. You get this sort of white calcium carbonate, which sort of looks like snow-capped peaks. Whereas the subduction that happens when a plate goes back down into the Earth, that's usually very deep, and so down there doesn't tend to be so much calcium carbonate on the seafloor. the way the Earth is sort of set up today, most of the subduction here is actually happening in the Pacific Ocean, which it's this big expanse of crust, and the crust is very old there, and there's not much calcium carbonate on that crust. Most of the calcium carbonate in the ocean is in the Atlantic, where the ocean is a little bit shallower, but it just doesn't happen that there's much of this stuff going down the drain in the Atlantic. So, maybe that's the way things normally are, but there are times when sediments that have a lot of calcium carbonate get shoved down into the earth. And one example is India crashed into Asia sometime in the last sort of tens of millions of years. And in between them was this shallow sea called the Tethys waterway. And it had calcium carbonate in the sediments. And then, when those two continents crashed into each other, there was no place for that ocean crust to go, even though there's, colder and denser ocean crust other places. It had to get out of the way, and so that carbonate got shoved down, and that was a time when the climate of the Earth was warmer. That was a warm time, because you're taking more calcium carbonate than usual and shoving it into the oven and letting the CO2 come out. So that's a way of changing the CO2 degassing rate and then changing the climate, sort of dial things up and down, like to make the dinosaur diorama people happy. Another one. What if we were to change the intensity of the sun? So this kind of speaks to the faint young sun paradox. Now we want to try to keep Carl Sagan happy. So let's say we make the sun a little bit dimmer by going back in time 500 million years and keep everything else the same. The thermostat, if it functions, what is it going to do to the CO2 concentration in the atmosphere? Will it increase it or decrease it? So let's think a minute. Let's say that the rate of CO2 degassing is going to be the same then as now, so we're not going to change that. And the rate of weathering has to be a slave to the rate of degassing, because that's where we're balancing the books. So that's the equilibrium that we're looking for. So we want to do the same amount of weathering as today, but we got less. The sun is dimmer. So how do we? So if you just make the sun dimmer by itself, and you keep everything else the same, what does that do to the rate of weathering? Make the sun colder. Come on, wake up. The weekend is almost here, but we got a few more hours. The rate of weathering depends on the temperature of the Earth, on water. So there's a high rate of weathering in a tropical planet, a low rate of weathering in a cold planet. So keep everything the same, but dial down the sun, the rate of weathering goes down. So now we're out of equilibrium, because we got more CO2 coming out of the Earth than is going back into the Earth by weathering. So the CO2 concentration, look at that, it builds up. Giving you the answer, sort of a negative feedback in itself, isn't it? Okay, so you'll be playing with, in fact, I think you'll even run a model to answer that exact same question in the lab next week. So you can kind of look forward to that. So now getting back to the carbon cycle overall, we drew a diagram last time that had the atmosphere kind of in the middle, solid Earth. We wrote that way, and now we've spent a lecture and a half talking about exactly how the solid Earth sort of interacts with the atmosphere. It regulates the atmosphere, it controls the atmosphere, but it does it very slowly on time scale of hundreds of thousands of years. And then there is also the land, which similarly kind of breathes carbon to and from the atmosphere, and the ocean. So I wanted to sort of fill you in a little bit on the land and the ocean. for the rest of today. So the clearest demonstration of the ocean sort of breathing is here. This is information from ice cores in Antarctica that go back hundreds of thousands of years, actually a little more than 600,000 years, and they tell us. Well, here there's one plot that tells the sea level, so that's the bottom wiggly line, and the top wiggly line is the atmospheric CO2 concentration. And so people who do, okay, so this is running time going from left to right. So here's today, and the sea level is at 0 meters today. I'll show you from over here. Sea level is at 0 meters today, and then back 20,000 years ago, sea level was lower than today. Boy, this scale doesn't look like it's right. Sea level was 120 meters lower during the last ice age. But also the CO2 concentration was lower during the ice age too. And this is thought to be due to the oceans. It's still not clear exactly how the oceans are doing this, but we can tell a few things. I can tell you a few things about how this seems to be working. So the oceans are breathing like the solid Earth breathes. Solid Earth, is a stable negative feedback. The oceans. First thing is that it takes something like 1,000 years for the ocean and the atmosphere to sort of come to equilibrium with each other. So the time scale for the ocean to affect the atmosphere is sort of 1,000 years is as short as it can go. And then it can go as long as something like, less than 100,000 years, because this is what the solid Earth calls the shots on 100,000 year time scales. So the way that the glacial cycles work is there are variations in the orbit of the Earth around the sun. So the Earth, sometimes it's sort of in a pretty circular orbit around the sun. Other times it's sort of more of an ellipse, and then the Earth is tilted. And so, we talked about this before, where on the ellipse the Earth, the northern hemisphere summer is found, and the northern hemisphere winter, and all that. Those things vary through time, and it's pretty easy to calculate how they varied throughout, a time span like this of hundreds of thousands of years. And the comings and goings of the ice sheets correlate really well with the way that the Earth's orbit has changed. It's called Milankovitch theory, and it works really, really well. So the orbit of the Earth seems to control the timing, anyway, of the ice sheets. So that's kind of cool. But now there's this other ingredient, which is the atmospheric CO2 concentration, and somehow there's some sort of an ocean feedback. There's some kind of a positive feedback. Where the carbon cycle over this glacial interglacial cycle, so these are shorter than 100,000 years. They're shorter than the the thermostat time scale. Somehow, when the ice sheets grow or the planet gets colder and starts to go into an ice age like it was 20,000 years ago, something about the carbon cycle in the ocean does this me too thing, this positive feedback, an amplifier. So yeah, you want it to get cold? I'll show you cold. I'm going to lower the CO2 and make it even colder. It's an amplifier. So the carbon cycle has completely changed its character. On the longest time scale, it's a stabilizer, but on shorter time scales, it's sort of an agitator. It's an amplifier. It makes climate changes worse. It amplifies them. And it's not clear how it does this. I was in graduate school studying oceanography when the first ice core data came out, or a few years after that, that said that the CO2 was lower during the last ice age. And we were all kind of really excited because we thought, you know, this will be easy. We'll figure it out. And you know, whoever finds it will get famous, figure it out. But it's still actually, after all these years, kind of a mystery exactly how the ocean does this. But it's kind of, if we want to think about how these two things fit together, you could sort of think about it like a thermostat in a house, maybe. So there's some CO2 concentration, which is the equilibrium, which is the set point, and so it kind of wants to get there, but it takes a long time to get there. And then there's something else going on, like, I don't know, the sun keeps coming out, and so sun shines in a window and heats the place up, kind of makes it get warmer, and then, you know, it tries to cool down, and something, you know, kind of cools it down a bit, and it sort of, the thermostat is trying to keep everything at a stable climate, but it's just kind of slow. So if you have something else going on, then you can make the temperature and the CO2 go up and down above and below this set point, but only for a limited amount of time. You can't do it forever because ultimately you got to balance the budget for CO2. So an intermittent sunbeam kind of works as an analogy for, you know, a thermostated house. But somehow it's the actual carbon cycle itself that does this, you know, unstable thing from the oceans at the same time as there's a stabilizing thing from the solid Earth. So a real analogy would have to be something like the furnace itself. Something about the way the thing works suddenly warms everything up terribly, and then the thermostat makes it cool back down, and then it kind of, so it's a quirky thermostat. It's not just a simple, you know, stabilizing at all times and all places. It's sort of got this kind of quirk in it. And we'll talk a lot more about ocean chemistry when we talk about uptake of the fossil fuel CO2, because this is where the fossil fuel CO2 will ultimately go. So we're going to sort of table that for now and come back to it. And then the third sort of leg of the carbon cycle is the land surface. So there's land and there are trees and, you know, roots and things like that. And then there's lots of carbon in the soils as well. So, you know, dead leaves that fall on the ground and get buried in the soil. So there's a lot of carbon on land that also interacts with the atmosphere. And so we saw the fluctuations in the natural CO2 concentration throughout the ice ages, but now there are also measurements of the carbon dioxide concentration today. And this is kind of the poster child image of the CO2 measurements today. So trees like like this are sort of set within the atmosphere, and there's sort of a boundary layer that the air right close to the ground is sort of it's sort of a stagnant layer, and it exchanges with the rest of the air in the troposphere sort of now and again, depending kind of on the weather. So if you were to sit here and measure the CO2 concentration, you'd get all kinds of, the trees are taking up CO2, so maybe you would get low CO2 values, or somebody just drove past in their truck and you get high CO2 values. You get all kinds of sort of local noise. And that kind of hindered efforts for a long time to decide if the CO2 concentration in the air was rising or falling. So this guy named David Keeling started making measurements on the top of the Mauna Loa mountain, the volcano in Hawaii. So this is a very high volcano, and it's poking way up into the sort of very, very remote marine troposphere. So it's trying to avoid this sort of local noise and get around that. And so here are the measurements, and you see that they kind of go up and down. There's this sort of 1-year cycle in the CO2 concentration of the air. So the vertical axis here is in our usual parts per million, and 1958 it was about it went from like 312 parts per million up to 317, and then back to 313, and then up to 320. And so it took a few years to figure out that the actual CO2 concentration was rising. And that's because of the annual cycle of trees. So trees take up CO2 to make leaves in the spring, and then they release the CO2. The leaves decompose, and the CO2 goes back into the air in the fall. So that's what leads to the seasonal cycle. Now the Earth has, the seasons are out of phase in the two hemispheres. So when it's summer in the north, it's winter down in the south. But then there's also an effect that it just turns out that there's more land in the north than there is in the south. So the south has Australia and South America, but the northern hemisphere has all of Eurasia, and North America is probably bigger in area than South America. So it turns out there's more land and sort of more of a seasonal cycle in the northern hemisphere than in the southern hemisphere. And the southern hemisphere, the seasons are out of phase, and so the cycles are kind of out of phase between the two. And here is there have been measurements of the CO2 concentration at a range of different places around the world. And so this plot here is going to show you all of the data from all of the different ones as a function of the latitude, which is going to be the x-axis here. And it's going to be animated in time. So this is the northern hemisphere over on this side, and the southern hemisphere on this side. So you see there's a much bigger seasonal cycle in the north than there is in the south, because there's more land in the north. And you can actually see the Earth breathing. It's just an amazing thing to me. You see these little spikes a lot, especially in the northern hemisphere. Those are caused by that sort of local noise. You just happen to get a blob of crappy air or something one day, but you can sort of see the larger, the seasonal cycle of the Earth breathing, and then you can also see the whole ball game kind of rising up, and that's from the fossil fuel CO2. If we had this kind of data from the year 1750, before there was much human activity, it would just stay in place and wag like that without doing this rise. The Mauna Loa is kind of right about here, I believe, is where the Mauna Loa data are. This sort of red point right here that if I point at it, it covers it up. So that data is this curve. And then the seasonal cycle is greater in the high latitudes. So you go to Alaska and measure this, you see a bigger seasonal cycle. Actually, you see the Earth, the biosphere breathing more deeply. The cycle is getting bigger with time, and that's because the plants are growing a little better now, maybe because of a longer growing season or more CO2 in the atmosphere or something like that. So then the really cool way to look at this this is a model of the CO2 concentration in the air, sort of in the free troposphere, so it's above this boundary layer, and you can it's a prediction of how the CO2 concentration varies throughout a year. So right now we're in winter, February, northern hemisphere winter, and so that means that there's CO2 coming out of the land surface from decomposing leaves and everything like that. So the CO2 is higher in the north than the south. The yellow color is higher than the blue colors. And then now May, June, we're just starting to get everything sort of springing into bloom now. And so you see these very low CO2 air blobs that are formed because the trees are taking CO2 out of the atmosphere in the spring and summer. So now we're in September, kind of the end of the summer, and it's kind of going back the other way. So where we go next in the class is to talk about fossil fuels and energy for a couple lectures, and then we're going to talk about taking some CO2 and putting it into this carbon cycle with these different sets of lungs.